Hello everyone, today let's look at Quantipus number 47, another combinatorics one, a really famous one. It's asking how many people do we need in a room to make the probability that two people have the same birthday more than 50%. So let's just say we have n people, then it's the question's asking us what's the probability that at least two of these people share the same birthday, and that's hard to calculate, so we're just going to calculate instead 1 minus the probability that no one shares the same birthday, which is just equal to this. So now if we have n people, how do we calculate this exactly? Well, this right here is just a combinatorics question, right? If we have n people in a room, the total number of birthday combinations that they could have is, first of all, 365 for the first person, because there's 365 days in a year. And for the second person, they could also have any of 365 birthdays, right? And basically, it's just going to be 365 to the power of n total combinations of birthdays that these people could have. Now, what are the combinations if we impose a rule that no one can have the same birthday? Well, again, the first person can have any of 365 birthdays. Then the second person cannot have that same birthday, so it's going to be 364, right? And we're going to go down the line, 363, all the way down. Now we know how this works. This probability is just going to be this divided by this, right? The number of restricted outcomes versus our total outcomes. Now let's look at some examples. For two people, the odds that no one shares the same birthday is going to be 365 times 364 on 365 squared, or equivalently 364 on 365. If I have three people, well, it's just going to be like this, 365 times 364 times 363 on 365 squared. So this is going to cancel. We're going to get 364 times 363 on 365 squared, and etc. So now for n people, this probability is just going to be 365 times 364 dot 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 all the way down to, it's going to end up being 365 minus n plus 1, as we can see here. And we had three people, we got down to 363, so minus 3 plus 1, same here. But that's just because this 365 corresponds to one person, but it's not actually decrementing. So now on the bottom, we're going to have 365 to the n, obviously. So now if we wanted to come up with a more concrete formula, obviously we're taking a product here. So we're going to use a product. Let's have k be our iterator. And we're going to want to take this product n times. So let's just have 365 on the inside for our denominator. And in the numerator, we're obviously decrementing by 1 every time. So let's take 365 and subtract off our iterator k. Now we start with 365, so k should start at 0. And then this is our final term. We can write this as 365 minus n minus 1 in parentheses. So let's say that k goes to n minus 1. Now this is the probability that no one shares the same birthday, right? But that's not what we're looking for. We're looking for the probability that at least two people share the same birthday, which is 1 minus this probability, right? So now we take 1 minus this fancy product we just calculated. So we essentially want to take this, and we were tasked with finding the smallest n such that this probability is greater than 1/2. Now, the only way to calculate this is just plug it into a product calculator or try and calculate it yourself with a calculator. And when you do that, you'll find that the n that satisfies this is going to be 23. And this is surprising just because this number is so low relative to how many birthdays there are, right? There are 365 birthdays, but it only takes 23 people for the odds of two people to share the same birthday to be greater than 50%. You couldn't find a way to do all this computation. Another really cool way, although much harder, is by thinking about these as independent trials. Basically, what we can do is we can say that we have n people, and how many pairs of people can we pull from them? Well, n choose 2. That's just going to be n factorial on n minus 2 factorial 2 factorial, and that's just equal to n times n minus 1 on 2. So these are the number of pairs of people that we can get, and each one of these pairs has a 1 out of 365 chance of having the same birthday. So what we could do is essentially model this as a binomial distribution. Let's say x is the number of matching pairs, and then we just kind of find the expected value of it or approximate it. Okay, I ran out of space here, so I'll make a new page. Basically, we're saying that m is the number of pairs that we can get from n people. So it's going to be n choose 2. And p is the probability that one of these pairs has the same birthday. Now we're essentially taking independent trials. So x is going to be roughly a binomial MP distribution. So the probability that x equals 0, which just means the probability that we have 0 matching pairs, well, that's just going to be equal to 1 minus the probability of any pair having the same birthday. And since we're kind of modeling these as independent events, we're going to take that to the power of m because that's how many pairs we have. Now, this is the interesting part. Once we have this, we can essentially approximate this using the property that this is roughly equal to e to the negative mp from calculus. This approximation here is accurate when p is relatively small compared to m, which it is in this situation. So if we model it like this, is the probability of no matches approximately. So the probability of any match is just going to be 1 minus e to the negative mp approximately. And we want this to be greater than 1/2. So that means we want e to the negative mp to be less than 1/2. That's just by rearranging this equation. Now, if we take the natural log of both sides, we have negative mp less than the natural log of 1/2. So let's multiply each side by -1. So I have mp greater than negative ln of 1/2. And since this is a log, if we are subtracting a log, we know that it becomes division inside. So I take 1 over 1/2, which is going to be ln of 2. So we essentially want mp to be greater than the ln of 2. So if we want mp greater than the ln of 2, that's just essentially the n times n minus 1 on 2 times 1 on 365. We want that greater than the ln of 2. So when we find the smallest n that does so with this approximation, obviously the approximation is going to be a lot easier than the big product. We also find that n equals 23 once you work this out. Now, obviously, there's no way you should just be expected to come up with a solution off the dome. I just found this online and thought it was pretty cool, so I added it at the end.